All right, in this lesson we're going to talk about calculating the standard deviation computationally, or as the undergraduate students affectionately refer to it as the fast way. There's just a few things that you need to know before we get started. So the first is, why is it called a standard deviation? It's called a standard deviation because it provides a common or standard unit of measure for comparing variables measured using different scales of measurement. So we're going to be talking about this a little bit later when we talk about something called z-scores. And you'll then get an idea of how z-scores and the standard deviation are very closely tied together. There's just a couple of things that you need need to calculate before you can start calculating the standard deviation. And I'll write them on the board here. The first one is, okay, and remember, we've always got to go inside the parentheses first, so that symbol tells us to square each of our x's and then sum them up. I refer to that as the sum of x squared. And then the second thing is what I call the sum of x quantity squared. So that says sum up all your x's and then square that sum. Up on the right hand side of the screen there, you see the formula for standard deviation. I will read that to you. Standard deviation is equal to the square root of the sum of x squared minus the sum of x quantity squared divided by n, all of that divided by n minus 1. So now it's just a matter of you kind of what I call plugging and chugging the numbers. The sum of x squared, how you're going to calculate that is by creating a new column of data where you simply square each of your observations. So 9 squared 81, 8 squared 64, 7 squared 49, all the way down. And so then when you get to the bottom of that, it's a column of data. When statistics, we like to sum up columns of data. So the sum of x squared is 385. Maybe prior to doing that, or whenever you're in the course of things you want to do it, you also want to sum up the actual observations. So 9 plus 8 plus 7, all the way down that column is 57. So we can start plugging numbers in. So our formula now becomes 385 minus 57 squared divided by n, which is 9. All of that divided by n minus 1, which is 8. Now what I've shown you is I have written down each one of those steps as I've worked down the page. So I have not kind of taken any shortcuts, if you will. Depending on your level of math skill, some of you won't need to write down each of the intermediate steps. On the graded homework, I will try to give you partial credit. So if I can figure out where you went wrong, I will give you partial credit. But if you don't show me any of your intermediate steps, sometimes it makes it difficult for me to actually locate that. So do what you feel comfortable with. Just be a very good housekeeper of all of the numbers. For this set of data, notice that we did find the standard deviation was equal to 1.73. This is the same set of data that we used when we were calculating standard deviation from a conceptual method. This is our computational method. So not surprisingly, we should find the same number. The second page of this document actually lines up and goes step by step the computational and the conceptual parts of calculating the standard deviation. But again, the main thing you need to recognize is that regardless of the method that you use, you should come up with the same answer. The conceptual method, again, really shows you how each score comes into play in the calculation of the standard deviation. This computational method is just a much quicker way. Before I let you go in this lesson, I do want to talk about something that I know your textbook talks about right along with the standard deviation. It's something called the central limit theorem. And I want to make a few comments about it. So listen, you might want to take a few notes because there's going to be some new friends that you're going to meet here. The first thing I need to define for you, though, is something called a sampling distribution. A sampling distribution is a theoretical frequency distribution. A sampling distribution is calculated or is formed by pulling multiple samples of the same size from a population. So, for example, if we have a population of size 10,000, we have all the names of everyone in that population in a big pot, and we pull out a sample of size 20 and ask each one of those people their age, add up all those ages, divide by 20, and we calculate the average age for that sample, and we write it down. We throw those 20 names back into the pot, stir it around, pull out 20 more names, ask those people all of their age, and write them down, find the average age for those 20 people, and we take note of that. Let's say that we took 1,000 samples of size 20, and for every one of those 1,000 samples, we calculated the average age. If we graphed those means, those 1,000 means, we have created a sampling distribution of means. Central limit theorem says that the sampling distribution of means will be normally distributed whether or not the population was normally distributed or not. So again, we have created a sampling distribution of means by pulling a large number of samples, 1,000, of size 20. We calculate the average age, if that's what we're measuring, for each of those 1,000 samples. We graph each of those means. We have created a sampling distribution of means. According to the central limit theorem, the sampling distribution of means will be normally distributed whether or not the population is normally distributed or not. When we create this frequency distribution of means, we might be interested in calculating also the standard deviation of that sampling distribution of means. When we do that, that standard deviation is called the standard error of the mean. So we'll be using these terms a little bit later, and it's probably fairly abstract, but I wanted to kind of introduce the concept of central limit theorem, sampling distribution of means, standard error of the mean to you. A couple other little things that are interesting about sampling distribution of means is that as the sample size increases, so let's say if the sample size of each of those 1,000 means went from n equals 20 to n equals 30, the standard error of the mean becomes smaller, and that sampling distribution of means approaches a normal distribution. And that is specifically when n reaches size 30. And so as you go through graduate school and perhaps get involved in some research, one of the things that you'll hear quite frequently is the importance of having a minimum of 30 subjects in your sample.